Good afternoon, this is Schweitzer, and we're going to run a little video here about just some ins and outs of gas stoichiometry and seeing how some things might be the same or how some things might be different. So let's run through a couple examples. Okay. Stoichiometry is linear proportions. Okay, that's a lot of what we're doing, just linear proportions, and those linear proportions can help us a lot. Keep in mind, 1 mole of any gas at STP is 22.4 liters. This is just Pfeffner, a condensed version of Pfeffner. That 1 atmosphere at 273 Kelvin is 1 mole. I should say, and it equals 22.4 liters. So sample question, a mole of zinc and a mole of hydrochloric acid react creating hydrogen gas. Estimate the volume. Okay, so this is a really good example here. Now we're in moles, so obviously our ice table is going to use moles. I got 1 mole of this, 1 mole of this. So, who's my limiting reactant? And at this point, because they have equal moles, twice as fast, this is my limiting reactant. I'll lose 1 mole of this and go to 0. At a 2-to-1 ratio, I will lose half of this one, so minus 0.5, and that would be 1 mole of HCl. Get rid of HCl and go to the zinc. At a 2-to-1 ratio is 0.5. 0.5. And the same ratio holds true for this guy. All right. Plus 0.5, and I believe at a 2-to-1 ratio here, also plus 0.5. Okay, so this is 0.5 left over, and 0.5 and 0.5. So estimate the volume of gas produced. So this is going to be an aqueous solution here, and this gas is the only gas that's produced. So I have, in this case, 0.5 moles of gas. And at this point, estimate the volume of the gas produced at STP. So we're going to just take this guy and run our linear proportion. Now again, we could do it 2 ways. One, just estimating. Well, if 1 mole is 20.4, then a half a mole should be 11.2, and that's what we're going to get. 0.5 moles, get rid of moles, and go to liters. 1 mole is 22.4, and that answer is 11.2 liters. Cool. All right, the next one is 2.6 grams of aluminum reacts with excess hydrochloric acid, producing hydrogen gas. Estimate the hydrogen. Okay, so now here we got aluminum plus HCl yields aluminum chloride. And I didn't give you the reaction, so you can try and write it on your own. Balancing this thing here, looks like we're going to get a 3 right here, but that's not going to work because I'm going to get 3 here. Can't get out of number. Let's double everything. 2, 2, 6, and then 3. Okay. Initial stoichiometric ratio n. Now here, interesting situation. We have excess of this, so we don't know how much we have. We have excess. 2.6 grams of aluminum, so that's not my limiting reactant. Okay, now aluminum actually is 26 grams per mole. I don't want to put the grams in there. That's a big no-no. Can't put that in there. So that here, if 2.6 grams is 1 mole, then if 26 grams is 1 mole, then 2.6 is a tenth of a mole. I'll show you the math. 22.6 grams to moles. 1 mole is 26. Divide out, you get 0.1 moles. So this is 0.01, 0.1, and I'm going to use all of it, minus 0.1 to 0. At that point, how much of this will I consume? A 2 to 3 ratio, well, it's a 2 to 6 ratio, or 1 to 3. 0.1 at a 2 to 6 ratio is 0.3. So I'm going to lose 0.3 of this. Whatever I happen to have, I'm going to lose that much of it. 2 to 2 ratio, I will gain 0.1 moles. And at a 2 to 3 ratio, I'll gain hydrogens. Let's do that. 0.1 at a 2 to 3 ratio. This is 0.3 divided by 2, so it's 2/3, 3/2 of that. 0.1 times 3 divided by 2, 0.15, which should make sense. 0.15, and that's moles of this guy. Moles of this guy. And 0.15. So 2/3 of it. Now let's go ahead and say, okay, attempt to estimate the volume of hydrogen gas. Okay, this might be a little tougher, but this is what we'll do. All right, I guess I gotta convert this guy to gas. This is the only gas. What's the estimate the volume? Again, so here's a couple options here. We could have two problems. One, this is like a balloon, taking place in a balloon, and the volume's allowed to expand. If we had a rigid container, then we could estimate the pressure. So one of the two options, if you have a balloon, it'll expand, and you estimate the volume, so that's what we're doing here. So we're STP, so let's do this here, 0.15, and we're going to dot line, get rid of the moles, and go to liters, 22.4. Now, a tenth of a mole would be 2.24. That's kind of where the estimating comes in. We want a little bit more than that, so it's going to be probably 3-4 liters. And let's do the math here. 0.15 times 20.4. 0.15 times 22.4 equals 3.36. Equals 3.36 liters. All right. And there we go. Okay. We have a pretty good little stoich problem involving gases and pressures. All right, another one here. So 10 grams of NaCl decomposes at 500 degrees Celsius at 0.5 in the container. So now we have a static volume, so we need to find pressure, and we're also not at STP, so what to do? All right, first of all, let's start a little ice table. Initial stoich ratio n, end. And notice this is solid, this is my only gas that I have. So I got grams, but I don't want to use the grams in the ice table. This thing is 5.8, I should say, 58 grams per mole. So I gotta get this into moles. Let's actually swap this guy out for 5.8 grams. I'll change that. We can make the numbers a little easier to estimate. Okay, so now this is going to be 1/10 of 58. So it's 0.1 moles is what I start with. This guy decomposes until everything's gone, 0.1. Down to 0. That's my limiting reactant, you might say. None of these to begin with, but I'm going to gain a half a mole of this, 2-to-1 ratio, and I'm going to gain half a mole of this. Okay. Again, to show the work on that, 0. Let's start from the beginning here. So you can see that 5.8 grams. Get rid of grams. I go to moles. 1 mole is 58. This gives me 0.1 moles. 0.1 moles, jumping from here to here. Get rid of the NaCl, going to Na at a 2-to-1 ratio equals 0.05. Okay, that's half of that. So half of that would be 0.05 and 0.05. That's the mole, half of the moles. So half of what we have, that's half of X, if you call it that if you want. So that's my actual moles. Now let's take a moment and let's calculate the pressure inside this rigid container and see what our pressure is. For that, because we're not STP, we really can't use any shortcut. Let's go right to PIV. PV equals nRT. I want pressure, so pressure equals nRT over V. N is 0.05. R, I'm going to go atmosphere, so 0.0821. And temperature, 500 Celsius. That's 500 plus 273 equals 773. That's pretty high. 773 divided by volume of 0.5 liters. Plug in your calculator. Let's see what our pressure is. It's going to be in atmospheres. 0.05, not that much gas, times 0.0821 times 773 divided by 0.5 equals 6.3 atmospheres. Yeah, that's pretty good. 6.3 atmospheres. Not undoable. I mean, the container can hold that, depending on the container. Alright, next one. Okay, so now we're going to run into just a general word problem. Take a moment, pause the video, try it out. Okay, so we're looking to run a similar problem. We have a balloon, so we're going to look for pressure. And we're running a chemical reaction. CaCO3 produces CO2 plus CaO. And this, of course, is a solid. Carbon dioxide, of course, is a gas. The only thing that we're really going to need there, I have 5 grams of this. So my plan here is to convert the grams to moles. And then, because we're balanced, looks like we're balanced here, I can just go moles of the CO2 is just a 1-to-1 ratio. And then I'm just going to use PivNert to convert this to pressure. I have to use PivNert because I'm not at STP. PV equals nRT. So 5 grams, grams to moles, 1. Adding that guy up, I believe we get to 100 grams per mole. Hopefully that's right. 100. And then it's a 1-to-1 ratio to moles of carbon dioxide, and then I'm going to use that in PivNert. 5 divided by 100. 100 is a tenth, but 5 divided by 100 is 0.005. So this is going to be 0.00, just 10. All right. 0.05 moles. Now we're going to convert this over to pressure. PV equals nRT. P equals nRT over V. This is 0.05, 0.0821. Temperature 298, that's the 25 degrees Celsius. Divided by the volume, which is, how large is the container be? So we're looking for volume. Let's back this up a little bit here. See if I can do that. Okay, we're not looking for pressure. We're looking for volume. Okay, so I got to read the entire problem. Volume equals nRT over P. And it's saying here our pressure for this is going to be 740, that temperature. So we're going to say our container can change, but we want to have a certain pressure. So it's going to be 0.05 times 0.0821 times 298 divided by the pressure, which is, they're doing torr here. So let's do this. Let's swap this out to 62.4 and put our torr in here, 740. And now we should get our volume to maintain that pressure with that gas in there. 0.05 times 62.4 times 298 divided by 740, and I get 1.25 liters. 1.25 liters. Alright, and there we go. Good problem. Alright, do I have to convert to moles in stoichiometry? Okay, so let's try this out once here. I got H2 plus O2 yields H2O. And in this case here, I have a 2. So I got to put a 2 here and a 2 here and a 1 here. So I got 2 liters of this and I got 1 liter of this. And how much would that get in liters? Do I need to go to moles for this? I know I do for grams, but liters of this situation. So let's try this out here. STP, so let's do a nice little math here. Initial stoichiometric ratio, and I'm going to use the moles and see what we get here. So 2 liters, get rid of liters and go to moles. 1 mole is 22.4. So 2 divided by 22.4 equals 0.089. So this is going to be 0.089. And it's the same math for the other one, 1 liter. So 1 liter, 22.4 to 1, so half of that, equals 0.089. 1 divided by 22.4 equals 0.044. All right, equals 0.044. One of my pet peeves, I almost did it myself, when you do work and don't put an answer by it, because that work is now useless. So make sure you put work by it so I know the work goes with that guy. 0.044. So, because if you're on a test or something, if you just put a number here with a work somewhere else and doesn't have an answer by it, then I can't correlate this work to this answer to that work, and therefore the work is no good. So, all right, so now I'm going to run this guy at 0. You'll notice I have him, well, which one's going to be limiting? So, okay, so this is going to be let's try this one, 0.044, 0, jump to here at a 1 to 2 ratio, so it's going to be 0.044. 1 to 2 is 0.088, so they're going to work out nicely. 0.088, essentially we're down to nothing. I have little rounding differences here. So with I might be able to answer my question right away. Do I need to go to liters here? You might be able to answer that right off the bat. 1 liter matched perfectly with 2 liters, which is going to give me plus 0.88 moles. And let's flip this back to liters. I did 212, 212, and 0.088. Get rid of liters and go to moles. 1 mole is, this is backwards, this is moles, and this is going to go to liters. So 1 mole is 22.4 liters, and you're going to get an answer of 2 liters. Okay, so in this case, do I need to go to moles and do gas stoichiometry? The answer is no. You can leave it in liters, as long as everything's in liters. If you only have liters, you can stay in liters, because you notice that this is a linear proportion. Volume to mole ratio is linear. Everything has this, every volume has the same moles, or moles have the same volume. So it's a linear relationship between here and liters. Mass, not the same. This guy's mass to mole ratio is different than this guy's mass to mole ratio. If it's linear, consistent, you can use it. But as long as everything is in liters, you can actually stay in liters. So 20 liters of this and 10 liters of this would give me 20 liters of this, because we're all in gases. So here's another example here, okay, where I'll pause the video, try it out. Which of these is true, which one's not true? Okay, just ran through an example of this, but we want to try this out. I'm going to move this up here while you guys try this out. Okay, which of these is true, which one's not true? Okay. Will 2 grams and 1 gram give me 3 grams? The answer is no. Okay. That is a stoich problem. These ratios don't measure masses. You may have 3 grams total mass, but that doesn't mean all 3 grams got kicked over. 2 grams and 1 gram give you 2 grams. No. In fact, it would have to be more than 2 grams, because you're going to consume, well, if you have 2 grams of hydrogen, that's limiting, which it isn't. Okay, the oxygen will be limiting, so it might be at least 1 gram, and then a little more because we have some hydrogen. Consume all of that. 2 liters and 1 liter equals 3 liters. Still no. No, because in this case it's 212. It's going to be 2 liters, not 1 liter. And 2 liters of hydrogen plus 1 liter of oxygen gives me 2 liters. Yes, this is the only one that really works. All right. Last little tidbit here. Why does pressure increase in a container? I mean, if you drove an internal combustion engine to school today, it's because inside those little pistons, they blow things up, and the piston gets shoved up due to high pressure. So in this case, what do we got here? We have 7 particles, okay? So in a container of acetylene is ignited. Explain using principles of kinetic molecular theory how and why the pressure, if the reaction is changed to its original. Now obviously pressure is the inside container. So I have a total of 2 of these. I'm going to draw these like little stars. 1, 2, and 502. So we'll draw that like this because that's what they are. 1, 2, 3, 4, 3, 4, 5. And I have 5 particles that are banging off the inside container wall. Now I got 6 particles. Okay, I'll draw these as a straight line. They're a dash, and we'll draw these like that. So I got 1, 2, 3, 4, 1, 2. So here I have 7 things bouncing off the walls, and here I have 6 things bouncing off the walls. In this case, my pressure will go down. You might say, well, that's unusual because When it burns, things generally explode up. That's due to the temperature increase. So as the temperature goes up, because heat's being released, then the particles move faster and they would bounce off the walls at a much greater rate as we're going from here to here. But if they cooled and they moved down, then the slower particles would bounce off. So if you had a enclosed container that could handle the explosion, all right, it would bulge at first, but when it cooled, it would really at that point start to condense and get smaller because of lower pressure. So the number of actual gas particles here is what determines whether pressure goes up or goes down at the same temperature. 7 versus 6. If it goes up, then you have more particles banging off the wall, your pressure goes up. Otherwise it goes down or it could stay the same. And there are the notes on that. All right, practice question, take a look, pause it. And the answer is coming. There you go. We'll stop there for today. Thank you very much.